All right, AP, welcome to your next lecture in Unit 5 Chemical Kinetics. We just talked about rate law and collision theory and understanding how concentration of specific reactants relate to the reaction rate. All right. But what I'm now going to talk about is a derivation of rate law known as the integrated rate law. And this, by the way, is calculus derived. Integrated integration is very much a calculus mathematical analysis process. So here's the issue with the rate law that I just introduced you to, is that by one, it requires initial rates and initial data in general, like initial concentrations and so forth, which is actually very difficult to achieve in lab and requires extreme precision in your lab instruments. In addition, the relationship examined or revealed through the original rate law, the OG rate law, okay, is that we get a relationship between concentration and rate, which theoretically is awesome, right? That's why we love the rate law, because it gives us the rate law constant, which is a constant that is unique to each reaction, revealing to us how the concentration of each relative reactant impacts, right, overall the reaction rate. But here's the problem, right? Chemistry has to be industrializable. It has to be money making. And when we talk about money making chemistry, we don't always want to know how concentration affects rate. That's not what we really want to know. What we really want to know from that is how concentration is connected to the time it takes. How long will it take me to produce this? So instead of figuring out concentration versus rate and then having to go from there and derive how much time it will take me to get to a certain amount of product, okay, what the integrated rate law addresses it expresses a relationship between concentration and time. Notice, I'm not talking about rate, molarity over second anymore. I'm talking about time. Now I can just go, boom, you want this much, it'll take me this long. Instead of saying, well, if the speed of my reaction is this, then give me like 2 months, right? This just gives us a direct relationship, boom, boom, from concentration to time. And so what we did, by we, I mean like better scientists that are mathematically more inclined than me, is that they did a series of calculus and like differential derivations on the rate law. And what it allowed us to do is it allowed us to determine how fast your rate changes. Okay. And so another way of saying it is, right, this is the whole thing with like integration. It's the rate of change in your reaction rate. Okay. So that's kind of what the derivations allowed us to do, allowing us to make a direct relationship between concentration and time. And the usefulness is that of this, which I've kind of already spoken about, is that we are able to determine the amount of chemical species present after a period of time. Okay, or at least estimate the time required to reach a certain point. In the reaction. So basically, let me just sum this up with one quick phrase, okay? Lab, production, and money making is why this is a much more valuable way to look at concentration and rate, because it gives us now the specific relationship between concentration and time through calculus derivations. Okay, so we have originally in the OG rate law, the original rate law, you had first, second, and third order, where third could only be achieved through the summation of the entire reactants order, giving us the reaction order. But now we have a slightly different shift, right? Because we're integrated. So those of you that are familiar with calculus, you know that when you integrate, you kind of go down one, right? Conceptually, you go down one. So now we have what we call is first order rate law and second order, but we also now have zero order integrated rate law. So let's just start with first and second because they're going to be more familiar with us. They cross over more. And then zero order we'll get into. So first order integrated rate law tells me, okay, 1 second. Let me just quickly zoom in on some of my notes. First order rate law, integrated rate law tells me that first order integrated rate reactions, okay, have a direct relationship between the concentration and rate. Okay, so here's an example of a first order, okay, first order integrated rate reaction. This is dinitrogen pentoxide, and it produces 2NO2.5 O2. Okay, totally recognize this as improper integers. This is actually taken from an AP book because what they're trying to show you is that I don't know how to explain this, but there are some cases when it's actually better in tabular data, like standard data, to actually have half coefficients. It goes against everything that you have been taught. Don't worry about it. Just focus on the application. So this is an example of a reaction, and what it tells me is that when I derive the first order rate law to get first order integrated rate law, what I get is this following equation, that ln of concentration equals negative K rate constant times time plus the natural log of the original concentration. So notice I'm talking about concentration. The concentration after a certain amount of time equals the rate law constant, still the priority, okay, the rate law constant times time to the negative plus the natural log of the original concentration. Or it could also be written as, if you want to use your natural log derivations, that the natural log of C concentration after a period of time divided by C original concentration initially equals negative KT. Okay, and so what we get right here is a very much a y equals mx plus b format. And what we then say is that m, our slope, is equal to negative kt. And what do you notice? We are able to easily determine the rate law constant through the integrated first order rate law equation. So still, K is still our priority. Determining the rate law constant is still our priority. But what we're doing is now, instead of doing it rate versus concentration, now we're doing it concentration versus time. And whether or not you're very familiar with integration and natural logs, the y equals mx plus b format is a dream come true for chemists, because what it gives us is when we draft things in y equals mx plus b, we now have, oh my goodness, we now have what we call a linear relationship, right? Which means we now have prediction capabilities, which is the ultimate goal for chemists, to be able to see the future in terms of the particulate level and behavior. That is the dream. So you're already seeing how the integrated rate law is just a really convenient, cleaned up version of the original rate law that includes variables that are more pertinent for us as we actually apply chemistry in industry, in production making, right? While still preserving the important information, the rate law constant, while still making it very easy for us to determine that almost conceptual constant, okay? So to summarize it in words, okay, it says that the natural log of concentrations gives us a linear relationship against time. So that's for a first order integrated rate law reaction, okay? Where we see a direct relationship between the concentration and the rate of change. So let's look at a sample problem of how we can apply this first order, okay? So we're given, calculate the time required to reach a desired concentration. Dinitrogen pentoxide, what we were just examining, is the unstable anhydride. Anhydride means like lacking water, right? Of nitric acid. Oh, sorry. Anhydride is, yeah, lacking water. Nitric acid that decomposes by first order kinetics into nitrogen dioxide and oxygen gas. As shown earlier in this section, and by earlier, I mean right above, okay? The rate law is rate equals K, concentration of N2O5. We really have only one reactant, like, right? So our rate law, original rate law expression has a one reactant. Okay. That's why our rate looks so simple. The rate constant for the reaction is 6.22 times 10 to the negative fourth per second. Okay. The units for a first order rate reaction. At 45 degrees Celsius, if the initial concentration of N2O5 is 0.5 moles per liter or molarity, how long will it take for the concentration to drop to 0.05? But essentially, how long will it take us to use up, okay, use up 4.5 of the concentration? Almost what? What is that? Like almost like 90% of the reactant, N2O5. How long will it take us to use up at least about 90% of that? Okay. So what we do is first and foremost, we need to recognize, okay, that the rate law that they give us does indeed, okay, tell us that or confirm that we are working by first order kinetics. Because when we say, when you're given that the rate, so this is original, right? This is original rate law right here. Okay, equals some constant, rate law constant, times the concentration of N2O5. There's an inherent 1 right there, right? Which tells us that the reactant order is indeed X equals 1 first order. So first and foremost, when you read a question, make sure that like you don't see any contradictions in the data they give you along with the extra information. So we are indeed working with a first order based on how they wrote this, okay? Okay, and then we're told that K is equal to 6.22 times 10 to the negative fourth 1 over seconds, or seconds to the negative 1, right? Seconds to the negative 1 per second. So what we do now is we say, okay, I'm working for sure, all the data, all the information confirms one another, and I'm working with a first order reaction. Now I'm going to integrate for this first order reaction, and I'm going to say, okay, well, according to my integrated rate law for first order reactions, I do some derivations, I get to natural log, and I get a linear relationship between now concentration and time. I extrapolate from rate and I go straight to time. And so what I do is I plug and chug. I know that the natural log of the concentration over the original concentration is equal to negative K times T, okay? And then technically, right, you'd have, let's see, plus the ln of concentration, of original concentration. Well, so what I get is, oh, no. Sorry, I'm like mixing up to the two equations. That's my linear equation simplified into natural log relationship. And so I'm using here, let me be very clear. I'm using this equation because it's just simpler. It's neater overall. It allows me to immediately isolate negative KT, my slope. And so what I do is now, I simply plug and chug. And I say, well, the ln, okay, of the concentration of 0.05 molar, and I'm not going to write all the numbers right now because I just don't have room, over the original concentration, 0.5 molar, is equal to negative K, so negative 6.22 times 10 to the negative fourth per second, okay, times T. And what I do is I plug and chug, I solve for T, and I get that in order to get to the concentration to drop down to 0.05 molarity, it will take me 3.70 times 10 to the third seconds. That's what my units end up being. I don't know how long that is in minutes, but that's a substantial amount of time, okay? So that's kind of one way that we can use this. And notice it's really convenient. If you're talking again to a buyer and you're like, how much do you need? How long before I'm going to run out of reactant? How long before that? I can plug this into the simple little derivative equation that's been derivated for you by recognizing one, okay, well, it's first order. So now that I've known that it's first order, I can once, you can find K using the original math process I gave you for rate law. And once you find those two things based on your previous lecture, you can then say, oh, handy dandy, I can use this derivative integrated rate law equation to directly go to time and concentration and figure out exactly how long before I might need to think about refilling, right, my sample or starting another reaction because my reactant concentration is getting low or so forth, okay? So go ahead and try this equation below for first order, and you're going to share in class. For this one, you will be required to do some anti-log calculations. So I hope that some of your previous math skills have informed you on how to do that. And don't forget that the anti-log of some number is like saying E to that number. Okay, so go ahead and try this and we'll share it in class. And let me continue on. You're welcome to pause me, but let me continue on in general. You still got more to go through. And just see why we love first order. So for first order reaction, we see that the natural log of our concentration after a specific amount of time is a linear relationship. So what this is showing you is how we can identify graphically first order equations. If you see on a graph that you get a linear trend when you're graphing ln of concentration versus time, you know that you're working with a first order reactant. So all I'm going to say here is be able to identify first order from graphs using integrated rate law relationships, rate law variables. That's all I'm going to say here. Okay. So let's talk now about second order integrated reactions, second order integrated reactions. And 1 second. So second order integrated reactions are similar concepts in terms of how we use them, but obviously a slightly different relationship between the concentration and the time. So for second order, integrated rate equations, such as the one below, we see, again, a one reactant based reaction. And we are told that it's second order with respect to that single reactant, nitrogen dioxide. So what we learn from this is, our equation, when we do some fancy dancy math, is we get an integrated second order rate law equation that tells us that the 1 over the concentration after a certain amount of time is equal to positive KT plus 1 over the original concentration. Again, giving us a y equals mx plus b format. But now your slope is equal to positive KT. Okay, so what we see is, to put it in words, is for second order equations or reactions, the second order integrated rate law tells us that the reciprocal of concentration gives us the linear relationship against time. So let's just hop straight into a practice problem. And I actually did not mean to say this one gets shared in class. Let's do this one together. So what we have here is we want to calculate the concentration after a given period of time for a second order reaction. Thus, we're going to use integrated second rate law in order to create a direct relationship for my second order reaction between time and concentration. So what I do is I read the problem. So nitrazole, nitrazole chloride, NaCl, is a corrosive orange gas that intensely irritates membranes in the human body, including eyes and skin. It decomposes slowly to form the gases nitrogen monoxide and chlorine, diatomic chlorine, by second order reaction kinetics with a rate constant of K equals 0.020 liters per moles times second. Given an initial concentration of 0.45 molarity, what concentration of nitrazole chloride will remain after 40 hours of decomposition? So first and foremost, you will probably want to convert, okay, immediately time 40 hours times 3,600 seconds per hour, okay? And that would give us an amount in seconds. So what is that? Oh, gee willikers. I need to do math. Hold on, guys. You know, I really should be able to do this mental math, but it is so early in the morning right now that I'm recording this that there's just no hope. There's just no hope that I can do this in my head. 144,000 seconds, okay? So this is the information I'm given. And really all you need to do is one, okay, look at this and say, okay, identify immediately, oh, I'm working with second order. Right here, that's what matters to me. So that tells me the type of integrated rate law as well as the assumptions I can make with this reaction behavior. Okay. And two, I need to identify, oh, they did give me the rate law constant for this respective reaction. They also gave me initial concentration, and I need to figure out, okay, end goal, what is the remaining concentration? So I'm going to go ahead and go immediately to my integrated second order rate law expression. And I'm going to say, well, I know that the reciprocal of the concentration after a certain amount of time is equal to KT, rate law constant, times the time plus 1 over the initial concentration. And all I do is simply plug and chug. And my goal is to find 1 over C, or I guess you could say my goal is to isolate C after a specific amount of time, the concentration after time. So all I do is plug and chug, and I say, well, I'm given the rate law constant 0.020 liters per moles times second, multiplied it times 144,000 seconds, okay, plus 1 over my initial concentration, which I'm given is 0.450 molarity. And what I get when I simplify all of this and I do all the calculations is I get that 1 over C, the reciprocal of concentration, is equal to 2,882 liters per mole. And then in order to find C, I flip it. And what I get is that C equals my concentration after 144,000 seconds or 40 hours is now 3.5 times 10 to the negative 4th molarity. Okay. And am I in the correct sig figs? Yes, 2 sig figs. So that is my final answer. Pretty easy when you think about it as being plug and chug. I'm really just asking you correctly identify the equation you need to use and then plug in the information you know to solve for the unknown, which is actually really, really nice. This is much simpler than doing all of that work with initial rate law, trying to figure out your reactant order and then your overall reaction order, and then trying to isolate and find your K, which you're totally going to be asked to do on the AP exam. But you're seeing how the value of this more developed version, integrated rate law, is so much more valuable for a chemist in the lab. Also, one thing I'm going to say again is you need to be able to identify second order reactions from a graph. So what you'll see is when you have a second order reaction, you will see a linear trend when you have 1 over the concentration versus time. Okay, so it's important to realize something, that most single reactant reactions, why did I say reactant reactions? Most single reactant, there it is. Most single reactant reactions, thank you. Thank you. That makes more sense. We're just going to combo those together. Most single reactant reactions are first or second order kinetics, therefore allowing us to use first and second order integrated rate law. Why is this? Because most reactions are faster, okay, at the beginning and then slows down as reaction progresses. Which I've already told you kind of makes sense, right? Because your reactant concentration decreases. And if you have less particles that can collide, you also just have less probability of collision, right? But then there is this special integrated rate law known as zero order integration. And zero order integration, okay, integrated zero order reactions has a unique premise to it. And that premise is that the reaction rate stays constant throughout the entire reaction. Okay, and is independent of reaction concentration. So when we derive and we use this integrated rate law, what we find is that there's a special category of reactions where actually the concentration doesn't have any effect on the rate itself. Okay. And so here is something to consider though with zero order reactions that are then integrated. There is a limitation. It only applies or is observed, right, to some, and dare I say few, reactions in very specific conditions. This is just like a special category of reaction rate, reaction orders, okay? This is just a very special category of reactions that display a very unique reaction order where when we integrate it, we see that there's actually no dependency on concentration, no relationship between concentration and the rate of the reaction, okay? So oftentimes what we say is that we'll use this integrated zero order reaction when we have reactions that are under conditions that make it act like a zero order reaction. So more often than not, where this zero order reaction concept is helpful is not actually when we see truly zero order reactions, because that's very, very rare. But when we are in conditions where a reaction behaves like a zero order, we call that pseudo zero order conditions or pseudo zero order reactions. Okay. And so this occurs when the reaction shows a reaction, I should say. A reaction shows different kinetic behavior, okay, under specific conditions, okay, allowing us, okay, to use zero order relationships. Okay, so pseudo zero order reactions are observed when a reaction that, maybe I should put in a qualifier, that isn't normally zero order, okay, shows a different kinetic behavior under specific conditions, allowing us to use the zero order relationship. And I'm going to put temporarily, right? Only for these conditions, right? So here's some other important implications to consider about zero order reactions is that actually these are other implications important to consider about all these reactions. First, second, and zero, okay? Is that we need to remember that only temperature or a catalyst can affect the rate of reaction. This is from your previous lectures. We already know this can affect the rate of reaction. Okay. Two, when we do talk about zero order reactions, a zero order reaction model can only be used or be applied for limited amounts of time oh goodness, my handwriting. Limited amounts of time under, right, specific conditions. Okay, so don't forget zero order is totally not common. Very rare and often is actually often observed by reactions that aren't typically zero order. They're just under extremely strenuous specific conditions. Okay. And then finally, one thing to consider about when you're looking at these integrated rate laws and trying to understand the relationship between concentration and time for a reaction is that it is, we commonly see in the presence of a heterogeneous enzyme, so like biochem people, we can often see a pseudo zero order or zero order behavior. Okay, so something to consider is in the presence of heterogeneous enzymes. So this is for all you biochem people, right? We can observe zero order kinetics. So that's just kind of a couple like extra little extension information on how to, well, focusing on zero order, but also things to consider when you're just looking and trying to identify whether you're looking at first, second, or zero order integrated rate reactions. So quick thing to note about the equation. What is the equation? What does the equation look like for a reaction that's zero order that theoretically concentration has no real impact on the rate of the reaction? What we get is this following integrated equation, that the concentration is equal to negative KT plus the concentration of original. Again, we see a y equals mx plus b, okay, relationship. And we ask again that you be able to identify via graph. Okay. If you're like, wait, that doesn't make really sense mathematically. I want to understand the math more. I'm gonna be really honest with you guys. It has been a long time since I have done calculus, and I personally have no interest in learning how to derivate this myself. I would encourage you to just take the conceptual information that I presented, understand that, be able to match it with the integrated zero order, or sorry, integrated rate equation, whether it be first, second, or zero order, and then be able to identify from graph. I'm going to be straight up with you guys. Like, please don't ask me to derive these equations. Like, please don't ask me to explain how does this like calculus concept go together. Like, I'm just not going to be able to answer that question because it's been a long time since I've done calculus. I've told some of you that like multivariable like made me cry. Okay, so I have buried that deep inside of me, that I've like repressed math inside of me. So I just ask that you guys, one, know what the value of doing integrated rate law. Like, why is it valuable? Because now we can go concentration versus time. Two, be able to identify and plug and chug with first order, second order, and zero order integrated reaction rate laws. Three, identify when you're working with a first, second, or zero order reaction based on graph variables. And four, be able to understand the specific limiting conditions where we would absorb the rare zero order behavior. That's it. That's it. Leave it at that. That's going to be plenty for you guys. That's going to be more than plenty, because you also have to remember how to do the long process of the original rate law, where we initially figured out the rate law expression that we then derived, right? So you have plenty to figure out. Do not worry about how do I derive this calculation? Don't worry about that. Just move on. So move on for your sake and my sake. So quick important thing to comment is that when we graph these integrated rate laws, you always want to graph it in such a way that you produce a linear or straight line, right? So important. The value of integrated rate laws, well, why did I say relate laws? Rate laws is the ability to graph linear relationships between concentration and time of a specific reaction. And then, of course, when we get a linear relationship, we are then able to solve for rate law constant K via the slope, right? So integrated rate law, again, is just making things easier. It's just making things overall easier for us. It's removing all the extrapolation details, all the difficult laboratory procedures, and it's just going straight to the heart of what we care about. Rate law constant, concentration, and time. How fast can I make it? How much money can I make, right? So here is a kind of summary for your slope. It might be helpful to do a quick summary. So I'm not going to force this on you guys. You can do if you want. Okay, go back to the rate law equations and just identify the individual slopes. You'll see that two of the rate laws have a similar slope where it's negative KT. Okay, but this is just something that you can use and a suggestion on how to study. Okay, is another quick trick that you can put in your toolbox for identifying first, second, and zero order integrated rate law. All right. Final thing I want to say is about rate laws, and then I'm going to jump into half-life, which is only for AP exam takers, is that notice we don't have an integrated rate law for third order reactions, right? And you're like, whoa, what happened to that? Okay, here's why. Remember that third order can only be achieved through the sum of the reaction orders. So, something that you're going to learn very quickly in future lectures is that there's actually no single reactant, okay, no single reactant that can demonstrate third order behavior. Okay, so that's just kind of like a quick caveat. If you're like, I still don't understand, don't worry too much about it. Don't worry too much about it. Just know that it's not possible because it requires more things than that are relevant for the integrated rate law perspective. Okay. Some things in chemistry, you just got to take it. Okay, 70% understanding. I'm going to roll with it and let practice teach me the rest. That's totally fine. You start getting gut feelings about just like, okay, that makes sense in chemistry, the more you work with it. So don't freak out too much. Just prioritize the math and the conceptual level that I did present you. Okay. So at this point in the lecture, if you are not planning to take the AP exam, you may now log off. You are done with this video. If you are planning to take the AP exam, I'm going to talk to you about one specific application of first order, okay, reactions. And that is known as half-lives. So a half-life, I'm sure you guys are familiar with from like if you studied like bio or anything like that and like evolution, okay, is the time it takes for half of a reactant's concentration to be consumed. Okay. We use half-lives when we talk about nuclear chemistry as well as geological chemistry, right? So the AP provides you an equation, and that equation is T half, that's the symbol for half-life, is equal to some constant 0.693 divided by the rate law constant, okay? And again, this is only we're only examining first order reactions. here. There is technically second order in integrated rate law for half-lives. Don't worry about it. The AP is not going to test you on that. The AP does not care about that. It just cares that you know the specific application of first order reactions relative to half-life. Okay, tracking, benchmarker, halving concentrations. Okay, so quick sample problem of how to solve these is, you're gonna love this, by the way. Quick sample problem is you can be given, okay, what is the half-life of reaction for this? Don't worry about cis and trans. You don't know what it means. All you need to know is that it is definitely a type of chemical. Okay, to produce a specific product of trans 2-butene gas, and you're told that the half-life is 0.00693 per second. Okay. Oh, sorry, you're told that the rate constant is 0.00693 per second, and you're asked what is the half-life. So all you do, this is so beautiful, is plug and chug. You want to find the half-life, and you're told K, you're given K. So all you do is plug and chug. You put the constant and you say, well, okay, I'm told that I have a K value, a rate constant for this specific reaction is 0.00693 seconds inverse. And when I solve that, I literally just get, okay, a value of, let me see if my math skills, is about 100 to 3 sig seconds is my half-life, given the specific rate law constant for this first order reaction. So it takes me 100 seconds to get through half, and then another 100 seconds to get through another half of my reactant species, and then another 100 seconds to get through another half, and so on and so forth. You'll see that the graph often looks like this, right? Almost like a curved decline, right? For those of you that it's been a while since you worked with half-lives. So B, I'm asked, okay, what fraction of the original cis-2-butene sample remains after 5 minutes of the reaction? So B, now that we know our half-life, now what we can do is say, okay, well, first and foremost, what is 5 minutes equivalent to? How many half-lives are in 5 minutes? So 5 minutes is equal to 300 seconds. So that means I have 3 half-lives present. So that means I go through 3 rounds of cutting in half. So all I can do, what's really, really easy, is I can literally just say, well, 1/2, half my concentration raised to the power of however many half-lives I have. So what I say is, well, 1/2 raised to the third is equal to 1/8. I have 1/8 concentration remaining. Ooh, baby. Okay, 1/8 concentration remaining. So that was really simple, really nice conceptually. Okay, next, C in this problem. What's C? C is asking me if the original amount was 3.45 molarity, what concentration remains after 7 minutes? Okay, so now I'm like, I see a relationship between concentration and time for a first order half-life reaction. Well, now what I can do, okay, I'm going to move this down below, is I can use my integrated rate law for first order reactions. And I can say, well, I know that the ln of the concentration after a certain amount of time is equal to negative KT plus ln C0. And I'm told that my rate, okay, is going to be, hold on. Okay, ln C is equal to negative 0.00693 seconds to the inverse times, and I'm actually going to put times, okay, my time. And by the way, I was told I have 7 minutes. So 7 minutes, okay, is equal to 400. 7 minutes is equal to 420 seconds. So times 420 seconds. So I cancel out my seconds. Plus the original concentration, ln of 3.45 molar. And when I solve for all of that and I do the anti-log, and I do the anti-log of ln C, what I get is that C is equal to E to the negative 1.67, which is going to be equal to, I have a remaining concentration after 7 minutes for the first order reaction of 0.188 molarity. And that is my answer, okay, for the concentration remaining. So let me highlight all my answers for you. There you go. So this is totally, again, an AP exam taker only necessity to learn about. And here's a fun summary table that hopefully the people that logged off early will see in their notes. Oops, forgot to mention to have them look at that. And here's just kind of an overall summary table. Remember, you do not have to learn about half-life for zero order or second order. That is not the issue. You're only caring about first order half-life. And you have several practice problems that you can do for you peers. This is kind of a summary practice that I'm actually going to remind myself that we're going to do this one in class. Okay, do in class. And then AP examiners, you have a few practice problems with half-lives in general. So best of luck. Good work, you guys. And you're pushing through. This is the last unit before the midterm. This is a very mathy unit. So for some of you guys, it's going to be very comfortable. For other of you guys, it's going to be very difficult. Please do not stress about understanding it 100%. Just focus on the amount of information I give you, which is plenty on its own, and learn how to work the equations. You've got it. Best of luck.